Many thanks, Professor Lee, for the very kind introduction. And I would like to thank the conference organizer for giving me the opportunity to present this keynote presentation with our work. So the focus of today is actually a good news. And the good news is that, as we have seen, the amount of installed renewable energy from various sources is increasing dramatically. These go all the way from wind turbine, concentrated solar thermal, and more from photovoltaic farms. Actually, the scale of this is quite considerable. If we look at the new installed electricity generation capacity per year, renewable energy is already here in blue and taken over by much other sources of electricity generating capacity. And just in 2020, more than 260 gigawatts of renewable energy were installed. This is about 80% of the totally new capacity added. And this is not the end of it. If we look at new proposed solar farms, this is an Australian one, their scale has already reached something like 20 gigawatts if it's going to be going forward. But there are new challenges with this. Obviously, how do we use this electricity when there is too much? How do we store it? And how can we use it at night or another time when there is no wind and there is not enough renewable electricity generated? Well, and one way to do so, and many countries, including Switzerland, are doing this since many years with nuclear energy. You can basically use a hydro pump to pump up water, usually fresh water, when you have too much electricity, maybe at night, and then you can actually release it during the day when you have high demand. However, this is not an approach that can apply to every country. If we look at the distribution of solar resources, which is one of the most abundant renewable energy sources, many of these countries don't have abundant fresh water. Take Australia. Should we use all this fresh water for hydro pump? We will not have it for agriculture or population and other means. So it would have a huge impact on the population and environment. Also, there is another issue. And the issue is that while the solar resources are distributed this way around the world, so mostly Australia, North, South Africa, and the west coast of the States and part of South America, actually the population is distributed very differently. Where we have the largest amount of population, we have relatively low renewable energy sources such as the sun. Furthermore, the high density of population make it hard to install large power plants, for example, in Japan or in Italy, where this land is already utilized for ancient cultivation like olive, tomatoes, and many others. So how can we export this renewable energy? Now, this is just an example generated from a country with low population density, such as Australia, which cannot use all this electricity, to countries that need it, all the way from Asia, Europe, and US. Well, one way to do so is to produce electric fuel. So the idea is quite simple. We can produce renewable electricity by various means, such as photovoltaics, such as hydro, and electric, and so on, or directly with the sun. And we can use this energy to produce a fuel, such as hydrogen, ammonia, and various other, store it, export it, and then release it, obviously, with an energy penalty, recover any molecule that we need. Like, for example, for ammonia, we may want to recover nitrogen, or for hydrogen, we may want to use water, and close the circle. This is actually already possible for hydrogen generation. We have quite an advanced photovoltaic solar technology, which is one of the cheapest ways to produce electricity. Electrolyzers already exist that can convert water to using the renewable generated electricity into hydrogen. And transportation for hydrogen is becoming more and more a reality. There are quite a few vessels already planned and they're going ahead. However, there is an issue. And the issue is that 95% of the world production of hydrogen is not produced by a renewable path using renewable electricity and water. Actually, it's done by steam gas reforming. And the reason is this is a big CO2 footprint. It also utilizes a fossil fuel. But the problem is that if you want to do it by water splitting, so in a renewable way instead, you have to use catalysts. And the process actually in itself is relatively simple. We have two reactions, an oxygen evolution reaction and an hydrogen evolution reaction on the other side. But to run this reaction efficiently, basically using well the renewable generated electricity, you need usually scarce materials such as ruthenium, iridium, platinum. And just to give you an idea, ruthenium world production in 2009 was about 30 tons a year. So if you want to scale up production of hydrogen, by renewable paths such as electrolysis, you need to change this catalyst because there is just not enough to replace fossil fuels. So one way to do so is to go from the rarest metals that are utilized for many catalytic processes to rock-forming elements such as iron, titanium, manganese, and others, which are actually abundant and can be found directly in the earth. However, when we try to do that, when we try to use these rock-forming elements for catalysis, such as electrolysis, the system becomes a bit more complicated. The reason is that once you have platinum, iridium, these are amazing material. They are stable, they have very high surface activity, they have very good electrical conductivity. However, when you start using something like iron oxide, the conductivity is not good. So you have to start engineering the structure that all the way from the surface to the microscale so that you're able to actually control both surface activity, making it efficient to split water, to actually transport of electrons, making sure you can do it at high rate necessary to obtain industrial capacity and not losing too much of this in the process. So the question is then, how can we scale material across multiple scale to produce effective electrocatalysts for water splitting and other e-fuels? Well, my group has been focusing on the use of fractals. Fractals are self-repeating structure that have certain similarity across various scales. For example, you can see this snow crystal, this ice crystal, this repeating fractal structure you can see in certain tree and shells. And the advantage is that most of these fractals happen in nature by self-assembly processes, which means by controlling the process, we can actually control the material over a magnitude of scale as required for the use of earth-abundant material for catalysis. Now, I have specialized in a particular way to produce fractals, and this is by using aerosols. The concept is relatively simple. We produce a nanoparticle, an aerosol, and then we let it approach a surface by Brownian motion. So it means basically that the movement due to Brownian motion is much more significant than movement by settling and other things. This is almost always happening where we're using nanoparticles because their Brownian motion is quite significant. When you do that, here is a particle dynamic simulation of what happens when this particle deposits on a surface. They start colliding with each other once they touch the substrate that is at the bottom, and they form this fractal-like structure, which actually are highly reproducible and repeat itself again and again. And by controlling the self-assembly process, we can obtain over very large surface, open structure with very high active surface area. You can do this simulation on very large scale, and you will notice that these structures are very reproducible. Basically, this is the same process as when it snows. Aerosol deposition can really coat mountains, and in fact, it's one of the most scalable way to produce high surface area electrodes of material. Now, how can we produce, however, this nanoparticle aerosol? One way to do so is to use flames. Flame synthesis is the first method humans have been utilized to make nanomaterials. If you look in history, an ancient Asian painting actually contained a pine suit. And the pine suit was done, as you can see in this small schematic here, by passing a candle close to a piece of paper rapidly. When you do that, the suit that forms is actually a nano pigment, or in the range of 300 to 500 nanometer. And this process has been scaled up through the centuries, with some notable mention, the carbon black, which actually was a water-soluble ink first, and then has become the main rubber reinforcement. 3-4 kilograms of nanoparticle carbon black are in each rubber, in each tire. And then we have fumed silica, a very important fluidide filler, and utilized in many processes, even in toothpaste, and pigmentary titanium oxide, which is the base of all paint, and obviously P25 done by a very similar process, which is one of the most established photocatalysts. So if we use flames for the production of nanoparticles aerosol, basically we can scale up the production of electrocatalysts for electrolysis and water splitting and other fuels very easily. An issue of the system that they're mostly gas-based, gas-fed. And by being gas-fed, you have limited control on the property of the nanoparticle and material you can synthesize. For the past 20 years, we have been focusing on the use actually of a liquid-fed flame system. The system works relatively simple. We have a liquid precursor, which may contain various cations of the material we want to produce, and it is a combustible solution that we can atomize in a nozzle as simple as this one. Usually the droplet size is about 10 micrometer. And then we can ignite it by a pilot flame, which comes from this ring around, and this will create the spray flame, which basically combusts the precursor solution. When this happens, the organic components are oxidized in CO2 and hydrogen, and you form a supersaturated metal vapor of the target oxide. This can be more than one. And then this actually nucleates the Kelvin critical size and grow by condensation, coagulation, agglomeration. And we can form very nicely crystalline particle continuously. This is an example of tin dioxide nanoparticle, an important semiconductor. And we have a very strong control on the particle size and crystal structure. For example, we can have the same rutile type cassiterite for tin oxide crystal structure and control the crystal size very easily from 20, 12, and 5, 6 nanometer. And this way we can increase the active surface for catalytic activity. Then we can actually go to the next step. Once we've generated this aerosol, we can use aerosol self-assembly to rapidly assemble such nanoparticle fins on surfaces. A unique aspect of this approach is that it's omnidirectional. Basically, this particle just deposited by Brownian motion and therefore can easily coat curved surface, rough surface, and form in a short time. This is 4 minutes, it can be much shorter, a very thick film. This is a film of about 50 micrometer. If we look at the structure of this field, we call the nanoparticles fractal networks because they form actually bridges and connection between the particles. And you can see a top view here and a cross section here and a magnification that actually resemble quite well the particle dynamic simulation I showed you before. And this has a porosity of 98%. And if it is no sintering, like in this case, if we let the particle coalesce and sinter during deposition, then we can control the porosity down. And this is often necessary to obtain more stable structure for use in liquid solutions, such as electrolysis. In the past year, we have actually investigated the use of frame aerosol synthesis of electrocatalysts with a wide variety of cation and an ion mostly oxygen and phosphor. But in terms of cation, we went into various transition metal, such as manganese and so on. And we have been trying to understand if by combining these metals, by creating more complex perovskite type of structure or ternary metal oxide, we can actually improve and optimize the catalytic activity for water splitting of this material and other processes. I'm going to show you a couple of them. One of the first material we investigated was manganese. It is one of the 12 most abundant elements. There is 0.1 in the Earth crust. If you just put your hand, you will actually have so much in average. And this is the evolving center of the photosystem II in plants. To give you an idea of the scale of production, we produced more than 10 megatons per year. So we have been trying to use flame spray pyrolysis, the system I showed you before, to produce well-controlled nanocrystal of manganese oxide with a spinel Mn3O4 phase. And we could actually control very well the crystal size as per the tin oxide, and also the specific surface area. To give you an example, we can easily go from large particle to small. This is important to study basically what is the correlation between active surface and actually particle size, and if they scale up when you make them smaller. And we can also produce directly highly crystalline structure and highly reproducible with a very small defective surface, which can be tuned by post-processing if necessary. And we can create a variety of polymorph species of manganese oxide, including manganese 203 and manganese 508. Manganese 508 is layered structure. Manganese 203 has been considered since a long time one of the most active species for electrolysis. And we want to do that by doing some simple post-processing, just annealing in air or in nitrogen, or in oxygen. And we actually compare the properties of these flame-made materials with wet-made commercial manganese 304 and manganese 203. And as you can see here, one of the first tests you can do is just placing these particles, dispersed into a water-containing solution with a sacrificial electron acceptor. This basically enabled the oxygen evolution and the removing of the extra electron. And if we do that, we can see that these particles are very active in producing oxygen, which is the oxygen evolution reaction. If you look at the amount of oxygen evolved per mole of manganese, we can see that this scales up quite a lot with a specific surface area. So our smallest nanoparticle are 300 times more active than wet-made commercial materials we could find at that time. And comparing actually different type of polymer, we see that polymorph with similar surface area have a similar activity. If we divide the activity per surface, however, we can see the Mn203 and Mn304 have a much higher activity than Mn508. And the reason could be that the Jahn-Teller distortion is actually present in both the structure, but not in these other polymorph. So this gives us also ideas on which material is more active. Also, we should note that when we scale up the particle and make them smaller and smaller, we can see that the surface become a bit less active. And this is interesting because you are supposed to have a similar activity per surface, and maybe due to the fact that actually there is not enough surface to both get the CAN acceptor and the oxygen evolution at the same time. Now, when we try to mobilize this catalyst on a surface and run water splitting electrolysis in a cell system, we can see, however, that Mn203 performs much better than Mn304 and Mn508. And the reason is that while the activity of the Mn203 and Mn304, the red and green, should be similar, there are other factors in places. In fact, electron transport through the material is also so important. And because the Mn203 has a better conductivity, it performs much better than Mn304. So this was just an example to show how important it is not to control only the surface of the material, but also the morphological structure in the microscale to optimize water split. Another example is a quite well-known photoelectrocatalyst and photocatalyst, which is bismuth vanadate. And here we investigated the synthesis of bismuth vanadate photoelectrochemical cells by flame synthesis, and we controlled the porosity of the material all the way from 98% to 80, 46, and 12 for water splitting directly from sunlight. And the 98% porous is not stable in water, so we didn't put it here, but 80%, 46, and 12, they all are. And the way we change actually this porosity is simply by changing the temperature during the deposition. An important aspect is that we produce all this structure with the same crystal structure and very similar surface properties, so that we can compare the effect of the porosity on the performance. We can also tune the optical density, so how much light is absorbed through the structure, just by changing the position time. So for the different porosity, we can have the same optical density, same light absorbed, and have a more fair comparison of the activity. And we have done that. And here we can see that the activity with a scavenger is actually much higher for the 46% porous bismuth vanadate. And if we put a co-catalyst and we perform water splitting, we can see that this is actually also the same. So the 46% reach about almost 1 milliamp per square centimeter during water oxidation. Why is this? We went to investigate this further and further, and basically we saw that there is a trend between the active surface, so the more porous, the more active surface, and the electron conductivity. So once we start making the surface higher, we start adding more resistive losses. And so we actually get much worse efficiency in converting light and transporting away the electrons for the oxygen evolution reaction. There is also another aspect, and this is not just electron conductivity, it's also surface. We have noticed that this bismuth vanadate made by flame directly is defective, so it doesn't have enough vanadium. So the stoichiometry is vanadium deficient. And the reason is that the high temperature make it so that some of the vanadium escape the surface during deposition. So we tried an approach which is similar. We deposit instead bismuth oxide, the bismuth vanadate, and then we do the one-step conversion in a wet solution to bismuth vanadate, obtaining a fully stoichiometric surface. And we compare these two structures. When you do that, you can observe that actually the stoichiometric bismuth vanadate has a much higher performance than the vacant one, and can reach easily about 2 milliamp per square centimeter during water oxidation. And this has been attributed to the important role of the surface in enabling actually an effective exchange of charges between the electrolyte and the surface of the electrodes. Another material I wanted to discuss rapidly that we have done by flame is cobalt oxide. Cobalt oxide is a very interesting and stable electrocatalyst, and it can be utilized for a variety of purpose, also as co-catalyst, for example, with a light absorber. We have been able to optimize the aerosol deposition approach to control very well the morphology and density and thickness of the cobalt oxide nanoparticles. So we made very thin nanoparticles deposited in FTO glass, as you can see here, and we've been able to grow them for 5, 10, 15 seconds. 15 seconds creates island with a height of about 200 to 300 nanometer. If we compare the performance as a function of time, here we can see the electrocurrent during water oxidation. We can see that when we start increasing the surface area by increasing the amount of deposition time, initially we improve the electrocurrent. However, once we reach 15 seconds, which is the island I showed you before, even if we increase further, it doesn't improve the performance anymore. And the reason is that this surface is not active anymore because cobalt is not enough conductive and basically just acts as a dead layer on the top of it. We also look at the long-term stability of this material, and what we could observe that after 1,000 cycles of CV, it was still actually performing slightly better than at the start, and after 12 hours was also quite stable. And we are now trying to extend this result to work with acidic condition, and we've been able to demonstrate with some modification of the surface a stable activity for more than 60 hours at 10 to 100 milliamp per square centimeter. Now, another thing I wanted to discuss is the feasibility of using approaches such as flame synthesis, not to coat only flat substrate, but to coat porous materials. This is an example of a structuring electrocatalyst, such as bismuth oxide made by flame, onto porous carbon fibers. And what happened here is that once we start using aerosol deposition, the nanoparticle reach a boundary layer around the material and then start moving by diffusion and Brownian motion. The beauty of this is because the aerosol is uniform, it will uniformly coat around these fibers. And you can see here that the same structure I showed you before can actually grow around a carbon fiber and form a very nice porous fractal structure. We have then applied this concept to electroreduction of CO2 to formate. So on the top, you can see the characterization of the fractal structure of our material. This is used by a very simple computational approach where we look at the image and we look at the density of the pixel over various scale. And that these end up into a fractal dimension of about 1.8, which is more or less what you expect for a cluster agglomeration during aerosol deposition. Slightly more dense than what you expect. It should be around 1.75, 1.8. And this is because this structure is slightly coalesced. To give you a feeling, a fractal dimension of 3 is a fully dense sphere. A fractal dimension of 1 is just a line of nanoparticles. If you look at the lacunarity, which is also another important indicator, shows when you reach the point of highest inhomogeneity. And the highest inhomogeneity is reached for the structure, around 150 to 200 nanometer, upon which the material becomes more self-repeating. We call this actually organized disorder structure. So it means it's highly reproducible on the surface. Now, if we look at the performance for CO2 electroreduction, and we look at the current density generated, we can see that this fractal structure, here in red, generated by the flame, produces much higher electrocurrent than if we were just taking the same particle and drop casting them on the same substrate. And this is attributed to the high surface area that we can reach with the fractals. If we look actually at the capability of this material to be selective for formate electroreduction, we can see that increasing the deposition time, we can reach almost 90% of selectivity. And this is attributed to the fact that this necking between the particles may be selective, actually, for the production of formate, reduction to formate. So this is also one to tune selectivity. However, selectivity often is not enough, and we introduce a new process to try to further tune it. This is, instead of using one flame, to use two flames. And one flame could produce, for example, as you can see here, one oxide. In this case, we're producing titanium oxide, but it can be bismuth oxide or silica. And the other flame can produce another material. In this case, we're using gold, but it could be another transition metal semiconductor. Now, when this happens, you produce an aerosol of mixed nanoparticle, which also assembly by the same principle, and are able to make a very uniform surface. If you look in this representation from my student, you can see we imagine to have, in this case, gold nanoparticle distributed on a fractal matrix of the metal oxide semiconductors. If we characterize this by TM, we are able indeed to determine the metal oxide and determine the presence of the noble metal, in this case, gold, but it could be another one. And if you look at synchrotron data sets on the fractal material porosity, we can see that we can preserve a porosity of up to 95% or 93%. We can decrease if we don't want, and the fractal dimension similar to the one I mentioned. And backscattering SCM images of the cross-section here and top view confirm the presence of nicely distributed islands of gold into a fractal matrix. When we do that, and we apply this to try to tune actually the selectivity of our reduction, we have another parameter, and the parameter basically is the presence of gold. And the gold, while not being photocatalytically active here, because we're just looking at an electric field, we have been able to determine that it can drastically increase the selectivity to formate. For example, at the right potential, which here is about -1, -1.1, we can reach up to 100% selectivity from the previous 90% that we have reported. And obviously, this has been achieved with gold and bismuth oxide. We can both identify this material. We are trying to understand why by electrical simulation of the structure. And we were able basically to see that the gold and the bismuth are able to focalize the electric field at the border where the necking happens. And because we believe that this necking is more selective for electroreduction to formate, we have been able to increase the selectivity through the structure. So here you see basically a nanoparticle distributed with a fractal structure simulated by particle dynamics. And here you see the electric field forming once exposed to a similar condition as in the electrode. The last part I would like to discuss is the scaling up of this technology for production of electrode for electrolyzer. And we have then investigated two approaches. One is to use a nickel foam, for example, or another substrate, which is stable, and just use aerosol deposition with as a backhouse filter to deposit on this foam, similar to what we have done with the bismuth oxide before. And then we have converted this to other than an oxide in a phosphide. So we have iron phosphide with a simple one-step process in a furnace. We can see that by doing this conversion, we can actually preserve the morphology. And if we look at the structure of the nickel foam, we see a similar distribution of the nanoparticles and nice coating as for the carbon fibers. If you look at the performance of the original iron oxide here in orange and iron phosphide for OER and for HER, we can see that actually the iron phosphide is much better performing. We can achieve on very large surfaces, the one I showed you before, a large current of more than 100 milliamp per square centimeter. And if you look at the stability of these materials for OER and HER, and we can see here that the iron phosphide is very stable, much more stable than the iron oxide, and it can operate for a long time at low potential. And we have been able to demonstrate under 50 milliamp per square centimeter just with one single sheet for more than 200 hours, both for HER on the right and OER on the right. And another approach I wanted to show is instead of using backhouse filtering to deposit on a foam, we can actually do a roll-to-roll production. Basically, we have on one side a rolled foam, which is our electrodes, and we have the flame at the bottom. We can use one or two flames, and we can let this roll through. And when we roll, we deposit the material on the surface. And this has been done as a demonstration just with an ethanol flame, so it doesn't produce nanoparticles, and it's a bit smaller, so that we don't we can film it better. But we have done it now as a tool for large-scale production of electrocatalysts. And with this, I would like to summarize my talk. And basically, I'm trying to show that using Fractal to engineer electrocatalysts is an approach, and very scalable approach, to obtain very well-controlled mass distribution, surface property, and optical thickness and density. And this can be combined with flame synthesis for the tuning and synthesis of a variety of materials, transition metal, also including noble metal if we want, but we want to move away from it. And it can actually lead to very active catalysts for hydrogen production, OER, HER, and CO2 electroreduction. Also, we believe many other electrofuels. And with this, I would like to thank you for your attention and for the opportunity to give this talk. Thank you.
Thank you, Antonio, for the great talk. Yeah. So maybe I get started with a few questions, and then I'll pick up questions from the audience. You mentioned that you can control the growth for the fractal structure. Sometimes it's just porous, right? But sometimes it's fractal. Have you studied, what is the synthesis condition at high level, right? So when you expect to have the fractal structure and when it's just porous structure?
That's a very good point. Thank you. So it depends from the coalescence and sintering. Whenever the sintering rate is low, such as for titanium oxide, then you usually tend up to end up with a fractal structure such as this one that I show you in this case. You have this fractal structure. This is simply because titanium oxide is a tough material, needs really high temperature. However, if you start increasing the temperature above a certain limit, then even titanium oxide would start coalesce and making a porous material. We have noticed that around the range of below 80%, 83%, we cannot find a porosity. We cannot find any more a correlation with the fractal material, but it becomes a porous material.
I see. So in terms of the catalyst activity, for example, right, so the functionality, is there any general understanding about is the fractal structure is preferred over just the porous structure or not? Or is it related to the dimensionality of the fractal structure? For example, on one slide mentioned that its dimensionality is 1.85, right? So if this number changes to a lower or higher number, this has a correlation with the dimensionality. Yeah.
That's a very, very good question. And actually, you just inspired me for the next paper. So we didn't study it yet. The difficult part is that you have obviously to compare as a function of the surface area. When you start increasing the fractal dimension, remembering that 3 is a fully dense sphere, so 1.8 is this aerosol deposition, and 1 is a line. So basically the surface area becomes less. So obviously we have to put more material or scale it for the surface. Also another challenge is that when you start doing this coalescence, for certain material you may change the surface. So we have to make sure that we can also have the same type of surface as the one done with a lower coalescence temperature. However, I think it's possible to do it for some few materials, and it would be a very good thing to study. One way we have done this more or less, it was by increasing here the time. By increasing the position time here, we basically increase how many of these fractals we have. And we noticed that this actually has an impact on the selectivity. And that's why then we did the follow-up study where we're trying to understand why it happens. And we noticed that by basically focusing the electric field into the necking more than the fractal structure, that's an important aspect. So I believe it seems like it's more the necking, so basically the boundaries between the particles, than the fractal structure inducing a change.
Thank you. And I think Drew has a question.
Yes. Thanks, Antonio, for this super exciting talk. I sort of follow on Xin's comment, because generally for transport, you want to have a fractal structure like our capillary networks. So I wonder if you can, maintaining the fractal structure while maybe coat or engineer the structure afterwards. So I think there is a, how much more modifiable, like by carbon coating or some way of improving the electronic conductivity can you do post-processing on the fractal?
That's a very good point, and that's a bit what happened here. So thank you so much, Drew, for the very good comments. So here we start with the fractal structure of iron oxide, and you can see it here in this example. And then we post-process it by placing it in a furnace with a nitrogen carrier flow and a phosphor source, and we convert it in a fractal structure of iron phosphide. And this is very important. Well, you can see here the cross-section, because the performance then changed dramatically. By having the same fractal structure, but by changing the composition, we could increase by various factors the OER and HER activity. And so I guess, as you mentioned, it is possible to use the fractal structure as a scaffold, which provide very good actually activity for mass transport, and then functionalize it. One of the things we have done in the past years, I've not shown here, actually it's not published because I couldn't yet bring it to the level I wanted, was to use ALD to coat on this fractal structure. And the idea was that ALD can enable us basically to make it robust, but step by step. So we can really see how we can transit and what is the transit to be sufficiently robust and at the same time active. And it is possible, just to give you a feeling, for titanium oxide, we had to deposit about 10 nanometer of ALD thickness to be stable for electrolysis in a water solution. Below that is not stable enough because capillary forces, unfortunately, are so strong that once you start basically being there, maybe it breaks when we take it out, not when we put it in, but it's very hard to know exactly if the structure can be utilized for electrolysis. But that's a very good suggestion. Thank you.
Yeah, another quick one. So when you do the dual flame, have the bismuth oxide and the gold, what's the change? I mean, is there any change to the selectivity of the formate formation?
Yeah, so it is actually a bit small here, so apologies for that. But if you look at the potential at which we run the CO2 electroreduction, you can see here we can reach up to 100% selectivity. When we had the bismuth oxide alone, which is here, we could only reach a maximum of a bit less than 90%. So basically, by tuning the combination of gold and bismuth oxide, we were able to basically be completely selective to formate production. We have some ideas about to, instead of using gold, use, for example, copper oxide and other materials as a tuning tool of the selectivity of this electrocatalyst for CO2 electroreduction.
Thank you.